Welcome to the workshop. Today we want to take a look at section 5.4, rooted trees. So we've already seen trees and we've already seen directed graphs. In this section, we want to combine the two concepts into the idea of rooted trees. So let's take a look at our notes. All right. So first, just an introduction of what a rooted tree is. A rooted tree is a directed graph that satisfies two conditions. The first condition is that we want to have something that looks like a tree. So if we ignore the directions that are on the edges, then the resulting graph is in fact a tree. The second condition is that there is a unique vertex, that the in degree of the vertex is 0 and the in degree of every other vertex is 1. Okay, so there's two things in that second condition. The second condition requires that one vertex has in degree 0 and that all other vertices have in degree of 1. All right. The vertex R is called the root of the tree. Excellent. So very briefly, just to make sure that we have an understanding of what a rooted tree is, let's take a look at some examples. So we're going to look at several examples that are not rooted trees, and then we'll actually give one really simple example that is a rooted tree. And in our next video, we'll take a look at more examples or another example of a rooted tree. So let's first draw a graph, a directed graph, that does not satisfy the first condition. So what I want to do is I want to draw something that that is not a tree when we ignore the edges, or when we ignore the directions of the edges, rather. And that's not too hard to do. But I also want to do it in such a way that the second part is satisfied. So I want the in degree of all vertices to be 1, except for one specific vertex, which has in degree 0. So this vertex has out degree 1, in degree 1, same as this vertex and same as this vertex. In particular, the in degree is 1. This vertex is, this edge is coming into the vertex. This in degree is 1, and this in degree is 1. The in degree of this vertex is 1. The in degree of this vertex is 1, and the in degree of this vertex is 0. So you'd say, all right, that's the root, except for when we ignore the edges, what we would have, ignore the directions of the edges, of course, what we have is not connected and therefore is not a tree. So this does not satisfy 1, so it is not a rooted tree. All right, now can I end up with something that when the directions are ignored, what we do have is a tree, but does not satisfy the second condition? Does not satisfy the second condition. I can actually draw such a directed graph. So I'm going to have 6 vertices here, 1, 2, 3, 4, 5, 6. And what I'm going to do is I'm going to give some directed edges, because a rooted tree is a directed graph. So that's what we're looking for here. So we want to not satisfy the second condition. And this actually does not satisfy either part of the second condition. So if we ignored the edges, ignored the directions of the edges, what we would have is in fact a tree. So that's fantastic. But the problem here is that the in degree is 0 here and the in degree is 0 here. So that identifies 2 roots, but there should be only 1. Also, the in degree of every other vertex should be exactly 1, and the in degree here is 2. So this does not satisfy the second condition for a rooted tree. And of course, it's not difficult to come up with an example that does not satisfy 1 or 2, either of the two conditions. And that would really just be an adaptation of this one that we can do. We already know that that one doesn't satisfy the first condition, or sorry, the second condition. So we can just add a couple of edges for it to not satisfy the second condition either first. All right, I'll get it straight. So let's give our edges. We know that this one is not a rooted tree because it doesn't have a unique vertex of in degree 0. Right, there's 2 of them. But when we ignore the direction of the edges, what we would have is a tree. So let's add a couple of directed edges. And now if we were to ignore the directions on the edges, what we would have is also not a tree. So this does not satisfy either of the two conditions. Now, I want to give a really brief example of something that is a rooted tree. So let's do that as well. So this is a rooted tree. So let's say I've got these vertices and some more over here. Now the in degree of every vertex is exactly 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Excellent. The out degree might be more than 1. That's cool. Doesn't matter. And then we have 1 vertex with in degree 0. So this would be the root. Excellent. So that's rooted trees. So in our next example, we'd like to continue taking a look at a different example of a rooted tree and then rewrite it a couple of different times. So that way what we end up with, or redraw it a couple times, so that way what we end up with is the representation in the conventional form for a rooted tree. So for now, thank you for your time. I'll see you guys back in the workshop very shortly.